Okay, let's talk about Newton's law of universal gravitation. What Newton said was that all masses attract all other masses. All masses attract all other masses. So in other words, what he said was that every mass attracts every other mass. So you're attracting the chair you're sitting in. Of course, because of Newton's third law, the chair is also attracting you. So that the fact that that always is going to happen. So what he said was, and then he said that force was proportional to the product of the masses. So in other words, it was directly related to how big the objects were, and then that does kind of make sense. What he also figured out, and this we did mathematically, was he said the force was proportional to 1 over r squared. R is the distance between centers. And then 1 over r squared, so it fell down. And it fell off as you moved away, and that makes sense, but it doesn't fall off linearly. It falls off as a square. This is called an inverse square law, and we're going to play with that some. Now, so, and basically we've all heard the story about, him seeing an apple fall from a tree, or feeling an apple fall from a tree, but then coming up with the fact that, hey, the apple's falling, the moon's falling. I mean, the brilliance is being able to make that leap into the next level. Now, when Newton died, what he left the equation was looking like this. The force is proportional to m1, m2 over r squared, and that's kind of where he left it. We can't have an equal sign because there needs to be a constant to make it an equal sign. That was not come up with till later by a man by the name of Cavendish. He did some really neat experiments. If you want to go look it up and see how he did it, you can. And what he came out with, F is equal to big G, m1, m2 over r squared. Cavendish was the one that came up with that big G number. Big G is actually a little number, 6.67 times 10 to the negative 11th. Newtons times meter squared divided by kilograms squared. And that's an experimentally determined number. Now imagine experimentally determine a number that's that small. That's not easy. So let's look at it. You could plug and chug a straightforward problem where you're just given all the values. You're given m1, you're given m2, you're given r, so you can square it. You always know g, and calculate that. And we're going to do some of those, but we'll probably do those mostly in class. Let's take a look now at the types of common things I can do with it. What would happen if I go to planet X, which has double the mass of Earth? So what would happen to my weight? Now, my weight is Fg. Well, Fg is equal to big G m1, m2 over r squared. The way to do a problem like this is put in what's actually changing. What's actually going to change is I'm going to double the mass of Earth. Whether you call the mass of Earth 1 or 2 really doesn't make a difference. But what I'm going to have is this G m1, 2m2 over r squared. Factor out what wasn't there before. I get G m1, m2 over r squared. Well, that's my old Fg. So therefore, I have twice the gravitational force, twice the weight if you go to planet X. Now what's happened? Let's say, well, okay, now let's so that's one case. Let's go with a second case. Let's say now that I go on an incredible eating binge and that I double my mass. So I spend a year eating everything I can get my hands on. Watch what happens here. Again, we start with this. F equals G m1, m2 over r squared. Now let's put in the new stuff. Well, G doesn't change. My mass becomes twice what it was. The mass of the planet's still the same. R squared is still the same. Factor out what wasn't there before. And I get that I gain twice Fg. What if I put case 1 and 2 together? So in other words, I'm going to double my mass and go to planet X. So now I'm going to say F is equal to, well, G doesn't change. My mass doubled. The planet's mass doubled. Wow. 4 times the old FG. Now let's play with distance, because this is the one that takes a little more thinking. So let's go with case 3. I'm going to double the distance. So in other words, I'm going to move twice as far away from the center of the Earth. Right now I'm 1 Earth's radius away from the center of the Earth. I'm going to go 2 Earth's radii. So now what I say is, well, F, G doesn't change, my mass doesn't change, the mass of the planet doesn't change, but now I'm doubling the distance, and it's important that the parentheses are there. So what happens is, I factor out what's not there before, I get 1 over 4. The rest of that is the old FG. So I lose 3/4 of my weight by going up to that distance above the Earth's surface. That's kind of cool. Now let's look at what happens with an inverse square law. It's kind of neat, because and it actually shows up in a few other concepts in physics. And what happens is, it says the force is proportional to 1 over r squared. So if I double r, 1/4 of the force. Triple r, 1/9 of the force. I see a pattern. If I quadruple r, I get 1/16 of the force. Now, let's go the other way. Let's cut r in half. If I have r, this is the one that takes a little bit of getting thinking. Let's go all the way back to the equation. I'm going to say F is, well, let's just do this. 1 over, now I'm going to say 1 over 2r squared. When I reduce that, I get 1 over 1/4, which reduces down to 4 times the old F. So in other words, it goes up by a factor of 4. So that's kind of important. It makes sense that as you get closer, it's going to go up. But when I take 1 divided by 1/4, that reduces down to 4. So therefore we'll play with that. Now we'll do some of more of these problems in class to get the hang of it as we play with it. But the key thing to understand is all masses attract all other masses. The force is directly related to the product of the masses. It's inversely related to the distances between the centers. So therefore, because take a look at a kind of an interesting thing out of that. We know that force is proportional to m1, m2 over r squared. So let's take 2 people that really don't like each other, and let's bring them together. We got, I don't know, somebody there, and they don't like each other. And we're going to make them hug. They're going to hug. And if they hug, what would happen is, that's going to go down. So therefore, F goes up. And that makes sense. The bottom of the fraction goes up. The F's going to go up. Well, as r approaches 0, F approaches infinity. So if you have somebody you hate enough and you hug them, you'll never be able to let go of them, because they do love them so much. Okay, have fun. We'll talk more about this later.